This is a production of Cornell University.
Thank you very much for the intro and for the welcome. I'm happy to be here, and partly because I've been kind of a sap about being back on campus after quite a few years, and yeah, it's beautiful to be here. So, originally I came to study mechanical and aerospace engineering, and I was hoping to study under Carl Sagan, but that didn't work out exactly. And then, but I did get to work with Steve Squires in Space Sciences on some of the early Mars rover development work there, and so coming from the aerospace robotics angle, ended up working on all these tools that had to do with soils and rocks, like the grinding tool on the Mars rovers, Spirit and Opportunity. I got to help design and build that and operate it when it was on Mars, and actually one of them still working on Mars now, and that was all because of the Cornell connections here. And then after a while I thought, so I was at a private company where we built that for the rover missions, called Honeybee Robotics in New York City. And then after a while I thought it'd be nice to maybe take a break from all that rocks and dirt, basically, and I figured I'd go to Carnegie Mellon to do robotic vehicle development work. And my advisor told me, once I was there, about this. It's exciting, Mars, like a lunar rover project to develop a new lunar rover. And then he told me what the task was. It was to support drilling down into the soils. So I started to wonder if this was a thread in my career that I was kind of inescapable. And then later ended up here now at this Near Earth Autonomy, which is a spin-off company from Carnegie Mellon, from the Field Robotics Center. And now, my major project at the moment is this agriculture project, and so we end up with a lot of this data where we're making these aerial observations on the crops and of the soils. So the thread continues, and I'm embracing it. I think it's great to be in the field. I think the other the more important thread, I think, is that I've enjoyed getting to work on systems that are collecting data for scientists to make progress in their areas. So this TERRA program has been a great project for us in our company to get deeper into the support of agriculture from an aerial sensing kind of angle. So I think just to give you a bit more of just a picture of what we're doing. This TERRA program is, it's led by Steve Kresovich. He's the PI on our project at Clemson. We are the team providing the aerial data collection and some of the analysis from there. There's also a team at Carnegie Mellon doing ground vehicles, so that robotic vehicles driving through the crops, collecting data up close to the crops. So we're combining these data collection platforms, outputs, and learning more about ways to accelerate the breeding process. So this is one of the fields. There are these exquisitely planted fields in South Carolina outside of Clemson. We're seeing hundreds of varieties of energy sorghum in this one 2-acre field. And so we're, well, at this point, I think one of the ground vehicles was driving, making observations on the ground while we're flying over. And I hope the 2 screens doesn't make anyone motion sick. Even one screen might be enough. So you can see a lot of variation in the fields. This is definitely not a typical farm, right? When you're looking at breeding plots, there are a lot of different traits in these different varieties. This is early. This is the first year out of 3 for this project. So we're looking at some of the early refinements of the breeding and refinements of the data collection techniques. So they have 2 fields in South Carolina. One's is right outside of Clemson, and the other is in Florence. So it's more, this you can see is this reddish clay soil, and the Florence side is more coastal plains, very sandy. So it's nice to be working the 2 different conditions. so down for a landing. So just for a little bit of background on the company I'm at now, we're about 40 people. It's about 4 years old. We're a spin-off from Carnegie Mellon Field Robotics Center. You can think of us as kind of this, the convergence of the standard aviation, where you're just basically flying. It's good technology, of course, but it's fairly simple navigation, usually flying waypoints, straight flight, fairly straightforward. Converging that with more of all the kind of intelligence that you're seeing more and more on driverless cars. The Field Robotics Center is actually a place that put out a lot of the people who are now at Uber and at Google developing these driverless cars. That came out of the DARPA Grand Challenges for these vehicles. So our group is a lot of researchers that came from that area, and so we're converging into this near-Earth autonomy. So basically, the company began where it's more focused on the navigation, helping aircraft fly on their own down near the ground where it's difficult. So we work in the field a lot. We work on a lot of different sizes of helicopters. This is kind of a cool shot flying up over Pittsburgh, seeing one of the rivers downtown. This is actually an autonomous flight with a full-scale helicopter there in the upper left. And flying a lot of different conditions. Even we're flying out over Lake Erie lately, helping a helicopter land onto a barge to show that we could operate from ships. So yeah, we work with full-scale helicopters, and also kind of getting into the more and more where I'm focusing on the mapping and inspection kind of work is in these the smaller kind of the 50 pounds and less, kind of that kind of category of aircraft where they're like these quadcopters and hexacopters, that kind of stuff. Now the technology is really improving. They're easier to use, and now the FAA has allowed them to be used commercially more and more. So it's all working together to become actually available. And so that's kind of where we're working in for our agriculture work so far. So as a company, we're working a lot in navigation, in mapping, and inspection. That's kind of the three kind of categories. I think we have kind of in our genes as a company this a history in agriculture. There was a fairly big project the USDA funded years ago where some of the founders were working on with specialty crops. This is all ground vehicle based, but making observations in the field with specialty crops and with nurseries and landscape industries. And so that's actually the connections, I think, with Marcel to Steve. And so now our current work is we're focused on this accelerated plant breeding, using the aerial reconnaissance essentially to help the breeding process, and also trying to spin that off into more farm management, helping growers. And so you could imagine we're kind of working with the kind of early adopters at this point, kind of breeding groups that are fairly high tech. Think of them, who function that way, and also some of the maybe larger growers that would be open to adopting this kind of stuff early. Mostly we're working with energy sorghum, but we're also looking some at maize and grapes. So this Boost is our team. It's our project under the TERRA program. There are 6 different TERRA projects, and so it's the Department of Energy's ARPA-E. It's their DARPA for energy applications, and so I think it's a fantastic program. The goal for TERRA as a whole is to support, to basically accelerate to this breeding process to get this really good potential of energy sorghum as a sustainable biofuel source, and also along the way develop new techniques for breeding, for accelerated breeding, and looking at high throughput phenotyping in the field as the main kind of method for that. So we're looking into, you're basically trying to support this development of predictive algorithms. You get data early in the growing season and predict the harvest kind of results. Be able to assess a variety really early. And then just get more of these detailed measurements of the plant physiology, and then focusing a lot on the data analytics and connecting the genotypes to phenotypes, that kind of mapping. So I don't know if this might give you motion sickness too, potentially, but we're trying to, you can imagine that this first theme, we're essentially developing these phenotyping hardware systems, getting them into the field so that they can collect data, both on the ground and in the air, taking these results and putting them in through an analysis pipeline, including machine learning techniques, and then doing this phenotype to genotype mapping, and feeding that all back into the field so that we have 3 growing seasons to work. So this cycle goes throughout the project. So just thinking about our activity in the field for this program, we've got these ground vehicles that Carnegie Mellon are making. They're driving through the rows, able to do this close proximity kind of sensing. You're right up against the plants. They're doing stereo vision, LiDAR, some other sensor types. And then they're also doing things that are contact sensing, which I think is pretty novel, where they're actually interacting physically with the plant. Measuring, for one thing they're focusing on right now is penetrometer testing on the strength of the stalks. So it actually has a gripper that visually automatically finds the stalk, grabs it, and does a penetrometer test, and as it goes through the rows. And then there's also a sensing network for environmental characteristics on the ground, and then we're the team that's doing the aerial sensing. So we've got this aircraft flying overhead, 40 to 60 feet kind of above the ground, doing mapping the whole field with a custom sensor package. So that's the bulk of our work, is developing this custom sensor package. We don't develop the aircraft, we don't develop sensors. We choose the aircraft for the purpose, and we choose the sensors for the purpose, and integrate, and then work with that data. Make sure the data can be fused well, it's registered well, spatially, it's calibrated well in terms of energetics, and bring that data together and make it useful. So this is a picture of our first sensor package for this project. It ended up kind of looking like a microsatellite or something. This is about 6 or 7 pounds. You hold it in your hands like this, and it rides on board the aircraft and is completely self-contained black box. Essentially like a very tricked out GoPro. You hit start, it records from all of its 6 sensors, and then also simultaneously it is estimating its position and orientation in the world as it goes. So that way we're not just it's not just flying over with a camera and then stitching together imagery later. That's fairly straightforward. It's actually it estimates where the sensor package is and how it's pointing, so that you can pull together really explicitly mapped. So every pixel exactly where it hits on the ground, and so you can make this very accurate maps, 3-dimensionally in some cases. So these are the aircraft we're working with. This is a 35-pound electric autonomous helicopter on the left. And then this is a similar weight. There's a hexacopter that we're using now. So we're kind of showing both. They're different categories in terms of cost and complexity, and also performance in some ways. The helicopter can get a lot more coverage over larger fields, faster, fly in more wind conditions. But the hexacopter is really easy to use. And so, I think most of the time we'll be operating from that. But so we tried to start kind of from, first principles in a way on deciding what was going to be in that sensor package. So we ended up going through that process. Ended up with these 4 sensing modes. So one to try to get at the shape of the crops, kind of geometric properties. We're experimenting with LiDAR. So it's it's laser scanner there. That's that disc kind of puck-shaped thing in the front. So it's scanning across the ground with infrared laser points and building up a 3D cloud. And then to get at kind of color properties and also geometric properties, we're using visible imaging, just standard RGB imaging, to look at temperature-related properties and some stress, plant stress. We're using the thermal infrared. So it's just monochromatic long wave infrared. And then to be a little more ambitious, we also added in a hyperspectral camera. So with typical camera, you think of color, it's three bands, right? Red, green, blue. You could think of them as 3 separate layers. Like if you really look at the sensor on a color camera, it's actually red, green, blue, and then another green. It's a pattern of 4 for everything that you think of as 1 pixel. And so you're getting those 3 separate bands. For hyperspectral, we're using a camera that has 100 spectral bands, and they're not overlapping at all. They're all separate, very narrow bands. And it's cutting across the kind of red end of visible and up into the near infrared, pretty far into the near infrared. So there's going to be, I think, we're taking a lot of inspiration from the remote sensing approaches from satellite, where they have all these interesting indices where they'll say this spectral band ratioed with this spectral band ends up correlating really well with this kind of plant property. And so there we're thinking that through this whole combination, hyperspectral in particular, I think we're going to get to explore and look for these properties, these predictive things, these correlations to plant properties, and be able to, I think we'll learn quite a bit, and then also get to do a second generation in the second year of this payload, where the sensor suite, where it'll be more refined and a bit cheaper too. So it'll be closer to being commercialized. So here's a shot of us. It's in the field. This is the Sandier site there in South Carolina. And there's the sensor package riding down below on one of the multi-rotor copters. So it's pretty straightforward. It takes just a couple people to operate in the field. It takes off and collects data all along, lands. Here's a shot of us, I think it was last month. I would lower the volume, but I don't know how. I tried. So you can see it takes off. It's really simple to operate this thing, even though it's a pretty serious aircraft in a way. I mean, it's still, you have to be very careful. We're following all the FAA regulations. We have registered pilots. Like the guy who's actually piloting this, he manually made it take off and then flipped it into autonomous mode for it to do its kind of simple lawnmower kind of pattern over the crops. But he used to fly Apache helicopters for a long time in South Korea. So that's him there, Spencer. So he's kind of unfazed by this stuff, luckily. So yeah, the flying portions is easy. It's just as long as you follow all the right procedures and keep everything legal and safe, it's all very straightforward stuff. It's not novel technology there. It's off the shelf. But all our focus is in making the sensor suite correct and making the data worthwhile. So here's just a series of frames just of what this. So it's all straight down-looking cameras. This is just some of the visible data from the RGB camera. And then just an example of what some of that looks like once you start to build these orthographic maps from the imagery. To get a sense of kind of resolutions we're getting, this was flying a little on the high side, about 60 feet above ground level. I was showing Steve some of the weeds on this shot. And then just better sense zooming in. So you're getting many pixels across a leaf, that kind of spatial resolution, seeing color variation, seeing texture in the panicles of these sorghum plants. Most of the time we're flying over energy sorghum, so the panicles aren't there, but in some cases we are. You're also seeing, we'll be able to be pulling out information about the leaf geometries, We're also seeing some lodging here as an example. I think that's something we could probably pull out automatically. And so then another data product is the LiDAR data. So this is this point cloud that we get. This isn't cleaned up or anything. It's just basically what it sees as it's flying. And so it's just a real 3D model. It's like flying around in a strange video game afterwards, right? You're just you can actually take measurements between points. So you're essentially able to just after the fact go through and measure geometric properties. So that later you get this 3D model that you can spin around, map in different ways, process in different ways, and get the 3D information. So those are some vans, vehicles, and tents here in that big open aisle. And so you're seeing a lot of the color variation. It's a color scale is applied just to visualize the differences in heights. So it's like a heat map for height. So you're seeing all these, a lot of these plots are, clearly are different varieties, and so you're seeing a fair amount of variation in the height by plot. That's actually one of the phenotype that we're focusing on these last couple of weeks is cleaning up a way to produce a good measurement of plant height, averaged out by plot. So this data kind of lends itself to that, to be able to know what your kind of characteristic height is for each plot and the amount of variation in height in that plot. And getting more and more appreciation for how that sounds easy but isn't easy. Just the idea of, I heard the story of, Steve Kresovich told us the story of a group with, there were, I think, maybe 6 pretty respected, faculty members on this one program, NSF program, and multiple of them were in the National Academy of Sciences, and it took them months to argue out how to measure the height of the plant. And now I understand that a little bit better. The idea of, if it has a panicle or not, does that influence your height measurement? Is a leaf pointing up or down? Does that mean the plant is a different height? Is the wind blowing things? What's your standard method of how a person would do it versus what can you actually do from the air? So this is, I think, we're getting more and more appreciation for some of these things, for the sensitivities. Here's just another shot of the LiDAR point cloud. These are the vans there in the top for scale. So as we fly, we're registering the data using GPS and inertial sensing within the payload. It's completely separate. It just is along for the ride on the aircraft. It's not interacting with the aircraft controls. We're also experimenting with targets on the ground to help tighten up the spatial registration even more. On the calibration, there's we work to some extent with what the manufacturers give us as far as the calibration of cameras, but then we're also doing our own quite a bit. In some ways, we're redoing and improving things that the manufacturers do, especially for the energetics on like the hyperspectral camera. We're doing things where we give different light source inputs, so doing lab calibration, then also field calibration, laying out tarps in the field, taking off and landing from a calibration target, more or less. And then we're experimenting some with with shadowing too. The intent there is just to make sure that the data is closely tied to the real physics of the plant, or there's real plant properties and aren't influenced too much by the changes in lighting conditions, which can be pretty significant. It would be like, like if you, with photography, right? If you're messing around with different white balances, you can imagine it being very different, and that's just trying to make things look appropriate. If you're trying to make physical deductions, then it's even more important. So with our analytics kind of support, we've got these kind of foundational things, ways of modeling what the ground shape is and segmenting into plots and annotating things, producing these raw data products, like just the standard things that are collected right off the camera, and then these reduced products, these image maps, 3D models, and then these more of derived data products is where we're starting to put more focus into now. Things where it's like phenotypes, plant traits, trends in these plant traits, and then we'll be supporting the rest of the team at Clemson, where Steve Kresovich's team is, and the Danforth Center, where they'll both be doing a lot of the effort of making correlations between the phenotypes and genotypes and feeding that into the breeding process. So I think I described those fairly well. I think just to get a sense of some of the other phenotypes we're going after, things like observing, being able to map out when emergence happens, where across the field, measuring the plant height per plot, and then how that changes over time, whether or not there's a panicle, and things like canopy closure, leaf area index, lodging, if the plants have fallen over, just other geometric types of things. Other stress, like water stress or nitrogen stress or leaf necrosis, and anything we can learn about the photosynthetic activity. I think from our hyperspectral camera, we hope to be able to pick that up pretty well. And other hyperspectral indices that could maybe have novel correlations that we'll find in this project. So in the end, I think once these become more refined, the hope is that we're giving advice to breeders, feeding into their analysis chains, and advice for growers too. How to better manage their fields, and so that they're not just given, like say earlier this week we had our people who were in the field in South Carolina. They came back with 1.3 terabytes, and they only flew I think 6 times. And so, a grower doesn't want that. A lot of us, they'll just be kind of blown away by that. It's just not useful. I think Steve and I were talking. They're busy already. They're not looking for a boring hobby on top of their job. So we're trying to refine this software process so that they're given something that's more like actionable intelligence, to use a term from that world. So it's just basically, what do I do? Give me advice. And so the ARPA-E program, TERRA, is really consciously pushing us to think about commercialization. We've kind of identified a lot of different potential ways that things could go. We could transition this technology to market. In the end, we're collecting a huge amount of data in the field. I think that could be valuable, just the straight data. The analysis algorithms could potentially be licensable. The vehicles and the sensing packages, and then also you can imagine the whole integrated phenotyping system of ground and air and analysis. And then I think we could very well make significant progress on actual, new, more refined varieties of energy sorghum throughout this project. So I think looking ahead a bit, we're hoping to extend the work onto other target crops. A lot of our sensor approaches and analysis approaches aren't completely specialized to energy sorghum. They could easily be applied to other crop types, or even other areas beyond specific crops, like surveying for disease in natural in trees. That's something that has been coming up in Pennsylvania area lately in discussions. So we're trying to line up more field trials with kind of large farms and smaller innovative farms. We've got people in the area, like Pittsburgh is such a robotics kind of mecca that we get lucky that there's a farmer in the outside of town who's just supports our work, so we get to operate there a lot, work with his on his crops. And so it's a nice example of that. We're going to be doing some breeding trials in Australia and trying to find a way to stay active during the winter here. So that we'll be there and outside of Melbourne this winter. So I think some good potentials there. And then, so this is a 3-year program with TERRA, and so we're hoping to continue that too. There's some potential there once some funding matching happens. So that could continue the work, make it more refined, maybe take in some different directions. So yeah, I think it'd be great to, if anybody had any questions, be happy to answer those.
Thank you very much, Paul, for offering any questions. I have a question.
Yeah, sure.
I noticed on the flyover that you showed us, it was a overcast day.
Mm-hmm, mm-hmm.
Does it matter? Do you prefer overcast versus sunny, or
Yeah.
sunny better?
Yeah, overcast is nice actually. It ends up with much more diffuse light, less shadowing. Yeah, it's kind of like, I guess, like doing photography. It's counterintuitive, maybe. But yeah, we don't really, we're trying to just get the processes right so that we can deal with either conditions, you know, with, but shadowing is hard to work with, you know, the idea of, if you want to see down into the crops, not just the top layer, then it gets tricky. It can muddy things for sure. Just you end up with dynamic range issues, you know, like a very well lit leaves and, you know, portions of the plant in some part of the scene, and then very low lighting on other portions. It's hard to get useful data across the whole range.
Yeah.
Mm-hmm.
When you do the, you can get a sense of the instrument package when you're flying over. Are you able to focus on particular quite small parts and get data from those? For example, to exclude soil, for example, plants, or to look at particular portions of the canopy. Can you do that?
Right. So
Get data from those?
yeah. So as far as the data collection goes, we are just covering the entire field, and we do it from two different directions. So we'll cover it, say like east to west, and then go back again north south. And so you get a fair amount of, you get very complete coverage, and then you get a fair amount of kind of penetrating observations, like down through, especially, you know, early and mid season, down to the soils and lower portions of the plants. And then, yeah, with the analysis, I think separating out soils from plant material is a fairly, I think, pretty straightforward thing that we'll be doing soon. And then it's hard to say how far we'll get to go with breaking out in an automated sort of way different portions of the plant. But my hope is that we could at least pick out panicle and leaves separate of the rest of the scene.
So when you do your thermal imaging for canopy temperature, so how will you do that? And what instrument, by the way, do you use?
Right.
For that?
Yeah. So that's it's fairly low resolution. You know, it's an imager from FLIR, company called FLIR. It's about 640 pixels across, and that's just because of the state of the art. You know, with color imaging, we have a 12 megapixel camera on board, but this was a 1 megapixel camera just because that's kind of the top of what's available right now. And luckily, a lot of the thermal properties in the field are fairly coarse. Spatially speaking, they're fairly coarse things. So I think it's still useful. And so I think early on, it might, say early in the season, it might be a little bit muddy where, pixels are overlapping a lot with, it'll be half landing on a leaf and half on soil. But later on, once the canopy starts to close, I think it'll be pretty clean sensing of canopy kind of thermal emission.
Is that what you use it for your stress?
Yeah.
Stress like that?
Primary. Yeah, I think we might get to see some in the hyperspectral too, but we're hoping to see the stress mostly in the thermal. Yeah.
How many flights over the course of the growing season do you do, and how do you decide to time them?
We are planning for about once every 4 weeks. We're also on the hook to show that we could operate more than one time a day, do full coverage of a fairly large field, like a 5-hectare field, twice per day. So that's more of a demonstrate to ARPA-E that we can do that kind of coverage. But in the real field, trips, we'll be there essentially once per month. It's a bit of, I think, at some point it would just be so close together that there wouldn't be much value. So that's, it was kind of a roughly chosen. We should be able to see quite a bit of change in 4 weeks. But I think later maybe in the third season, we're hoping to just keep the system, keep the aircraft down there at the field, and it could be operated more frequently than that. So yeah, we could experiment some to see if there's more utility in more frequent trips. Yeah.
Do you have any plans to utilize this technology for soils, for example, and then secondarily things like pests and diseases?
Right. Yeah, completely. I know I think I'm hoping to talk more about some of the soil potentials. It'd be nice to hear some advice from you on that. I think it's especially when it's large areas to survey. It's the aerial approach seems really good for that. So I think there's a good potential there. And then we've had some first conversations with some people about some of the pests, pest management, and I think it could be. I think a lot of ways we'd maybe be observing. I think we've seen on the ground. We're actually the ground vehicle is actually seeing aphids in the images, actually picking out things, able to recognize them. But from the aerial point of view, we'd probably see more of the effect on the plant, which would be slightly indirect, but still, I think, valuable. Yeah.
What aspects of the soil?
We haven't actually been considering it in depth yet. I think there's good potential for it, but I think just to see changes, seeing motion of soil, if there's the 3D data is so good, from our LiDAR, that I think if you're able to see any redistributions of soil, I think that could be really good for picking that out over time. We've done stuff where you could see small changes in a scene just from one flight to the next, that kind of thing. But then also with the picking out things like color and thermal and hyperspectral, we might be able to see other processes that are going on in the soils. So it'd be nice to hear advice on that. Yeah.
Thank you for the talk. I feel like you come from the future. So I found it really exciting. Can you talk about the sensing technology to differentiate different crops? So you've been working with sorghum a lot.
Right.
Do you have the technology now to differentiate it from corn?
Yeah, that's a good question. You're right. We've been focusing on just this one, all these different varieties of sorghum, and it's more. Our focus has been more about the kind of basic traits, but I think actually Steve and I were talking this morning a little bit about trying to differentiate crops from weeds, and so I think we were talking about different methods for that. I think from this high resolution camera, just visible data, we could get at some of the geometric properties. Say some characteristics that are pretty reliable, like the shape of the leaf or the way the leaves are branching. That sort of thing could be a pretty reliable way to differentiate between plant types. And then also, I think the spectral signatures could be potential on that. So where just something a good correlation. Say, something has some kind of spectral signature in the infrared, maybe in the near infrared, that say corn to sorghum is very different. So it's something we haven't done, but I bet these types of sensors could maybe do it though. Thanks.
Just one kind of following up on Sue's question about the timing. I mean, you might consider for your stress and photosynthesis measurements, you might have to think about doing more than one pass.
Yeah.
Over the course of the day,
Mm-hmm.
if you want to optimize, timing for identifying differences.
Yeah, that's nice. Mm-hmm. Yeah, I think so. I guess saying once that's good advice. I think we've been going to the site once per month, but like say this week, for instance, we had some flights kind of late afternoon on one day, and then kind of earlier morning. I guess it was more midday the next day. So temperatures and lighting conditions were different, but still, the state of the crops was essentially the same. So that's probably you're right. That's something that would be probably good practice. Yeah.
Thinking about commercialization for growers in these businesses, how would you imagine that would be licensing the software and having someone come in with the hardware or selling
Right.
the hardware, or
Right, sure. Yeah, well, we're trying to work on kind of 3 different, business models, really. From our company's point of view, I think licensing the software is probably the quickest and easiest way to market. But selling an integrated hardware package, where it's the whole thing, basically the aircraft and the payload, or selling just the sensor payload, those are very viable too. Most of the, I think it's really hard to get much revenue from, or to get much profit, I guess, from just selling hardware packages, really. But selling it more as a service, I think, could be actually better in a lot of ways, because a lot of the end users don't really necessarily want to get into operating these things or dealing with owning them, maintaining them, and all that. But they like the data, so just for them to hire a service to come in and collect the data and give them the data is probably a really nice model. I think in that case, our company we would be the technology developers and owners of the intellectual property, but another service providing firm would probably do that. So those are probably the licensing and the servicing are probably the 2 models that are probably the most likely to work out well. And then as far as costs, on the aircraft side of things, it's, that helicopter we're working with is something like, $60,000. Then the smaller one, or not really smaller, but the hexacopter one is more, it's more of a standard product now. It's more, commercially available broadly from the DJI. That one's about $15,000 if you get for all the hardware needed. So that's a lot more attainable for people, and then especially growers. And then the sensor package, we're looking to get that down from like a very ambitious, the one we're working with now is something like $75K for just the hardware, right? Not the labor to build it or get it running. But then second generation, we're going to bring that down, probably more like 40,000 in hardware, and then a commercialized version of that down even further, maybe hopefully more like 25. Or maybe even lower, with numbers, with manufacturing scale, that could go even lower. So.
Well, Paul has told me that he does maybe have a few slots open on his afternoon schedule. So if some of you would like to have a longer conversation with him, you could come up and maybe schedule that with him if he still has time available.
Yeah, that'd be great. Any advice or questions? That'd be great.
And we really appreciate your coming. Thank you once again.
Thank you.
This has been a production of Cornell University, on the web at cornell.edu.